In this video, we're going to talk about one particular method of volume by slicing, which involves revolving a region about an axis and using cross sections that are discs and washers. The PowerPoint that I'm using for this presentation was prepared, I believe, by Greg Kelly of Richland, Washington, and I accessed this PowerPoint via Linda Rajat, a math teacher on Vancouver Island in British Columbia. So let's start with the curve y equals root x, and I'm going to take that and I'm going to revolve the region between 0 and 4 around the x-axis. And what's going to happen is if I run my rectangles vertically and revolve them, I'm going to get, as a cross-section, a disc, sort of flat cylinders, a circle with infinite thickness, which we call a disc. And the volume of each of those cylinders, or discs, would be the area of the circle, pi r squared, times the thickness of the disc. And so in this case, the radius would represent the y value of the function, y equals root x. So if you're getting a given value of x, you plug that value of x into the root, and you get the radius. So our equation becomes pi root x squared. And the thickness is a piece of x, so that's dx. And if we then sum up all such cylinders from 0 to 4, we will get our volume. So you can work this expression out algebraically, as you're going to see down below here, or you could do it with a calculator, and you would end up getting a volume of 8 pi. So this method of slicing is called the disc method because the shape of the slice you get is a disc. And so if we're rotating a region about the x-axis, the following formula would apply. The volume is pi, definite integral from a to b of f of x squared, f of x representing our radius, dx. You can also rotate shapes around the y-axis, and that would put our integral in terms of y. So just an example of that. We have the function x equals 1 over root y. So we'll just build a bit of a table of values for that, since that's not a function we readily know. We have our area, our region in blue, and we're revolving it around the y-axis. Now the important thing to remember with this method, as with any slicing method, is that our cross sections run perpendicular to our axis of revolution. So our rectangles, which create our discs, are running horizontally here. Alright, so there's one particular rectangle, infinitely thin. It's got a thickness of dy. Its radius is an x distance, but x is a function of y. And we have our x isolated as 1 over root y. So 1 over root y will be our radius. And so putting it together with our formula, pi radius squared, which is our circle, our cross-sectional area, times dy, which is our thickness, gives us the volume of an individual disc, and then we sum them up from 1 to 4. And then we evaluate the integral. To get 2 pi ln 2. Alright, let's look at another example. This time we're going to take a region bounded by two curves, x squared and 2x, and we're going to revolve that region about, in this case, the y-axis. So what you're going to get is a hollowed out, kind of a hollowed out parabolic reflector. Okay, so kind of parabolic on the outside, and on the inside a sort of a cone that's been cut out of it. Okay, so if you can try to visualize that. And so we want the volume of that So again, because we're revolving around the y-axis, our rectangles run perpendicular to the axis of revolution. So we use a horizontal slice, which is there. Now what's going to happen this time is the disc now has a hole in it. So it's kind of like taking the outer disc, which we did in previous examples, and then subtracting an inner disc. And we call this a washer. So the volume of the washer is going to be the pi r squared thickness of the outer disc minus the pi r squared thickness of the inner disc, which I can write as you see here. The thickness is a piece of y. The big radius is going to be the x distance going out to the rightmost function. Now you'll notice that our functions have y isolated, and since our radius is an x distance, we need to have x as a function of y, so we're going to need to isolate x in our two equations. So here we are doing that. And so my outer radius is going to be x equals root y, the x distance of that particular function, so the radius will be root y for big R and y over 2 for small r. Putting it all together and going through the evaluation process. You can look at that on your own time, work through that. 8 pi over 3. So this application of the slicing method is called the washer method, as we said, just because we're taking the outer disc, subtracting out an inner disc to get what looks like a washer. And if you were doing revolution about the x-axis, previous example was revolution about the y-axis, then your formula would be set up similarly, looking like so. Alright, let's do the same example from the previous example, except this time we're going to revolve our region between the two curves about a line that's parallel to the y-axis. So it's like revolving it around the y-axis, but it's not the y-axis, it's a line parallel to the y-axis. X equals 2. So there's x equals 2, where we're going to revolve it, and you can see now the shape is going to look different. It's going to have a different volume because we're revolving at a different distance, but you can see the washer showing up. So again, we want to do the outer disc, subtract the inner disc. Now the outer radius is a little trickier this time. It's going to be 2 take away the x distance of the line from the y-axis. And the inner radius is going to be 2 minus root y. And then we apply our same formula, pi radius squared minus pi radius squared times thickness. So here we are putting it together, and our rectangles are running from y equals 0 to y equals 4. So our limits of integration are 0 to 4. Set it up. And I'm just bypassing all the work because that's stuff you know how to do already. And you could also just plug the formula into the calculator to get an answer. Although, of course, you won't get an exact answer necessarily, depending on what it is. 8 pi over 3 would not be exact on a calculator.